Good evening. We will start in like 2-3 minutes. Let's start. So, welcome to week 5 of the live problem solving session for the course Fundamentals of Semiconductor Devices by Professor Digvijoy and Nath. Course code NOC 25E39. A little bit about me. My name is Mayank Goyal and I am a research scholar at the Department of Electrical Engineering, IIT Bombay. About this course, it is being taught by Professor Digvijay Nath, who is an associate professor at IIC Bangalore. For week 5, we have studied applications of PN diodes, breakdown, Zener and avalanche breakdown in PN diodes, capacitance voltage profiling of PN diodes. Then we shift to new kind of devices which are metal semiconductor junctions, which are ohmic and Schottky contacts. Then device applications for Schottky contacts, Schottky diodes. So generally we are having this session every Sunday 6 to 8 p.m. But for next session there might be a timing change. We might do it on Saturday or something. And this is the Google Meet link. So as always, I will be sharing some practice questions with you. Practice questions which you can which will help you in solving the assignments as well as the exam questions. So let's start. The first question: when photons are generated in a photoreactor, what do they generate? Heat, electron hole pairs, magnetic fields, sound waves. Who can answer this question? If you know the answer, please speak or write in chat. That is right. The answer would be electron hole pairs. So, what happens is that when we shine a light, the the valence band will absorb a photon, and this will result in and excite an electron, which will shift from valence band to conduction band. This is called generation of electron hole pairs, as we also learned in last class, last session. So, next question: what is the main purpose of a solar cell? To detect light, to emit light, to convert light into electricity, to store electrical energy. That is right. The answer would be to convert light into electricity. So you see, a solar cell is basically opposite to in functioning to an LED. A LED, in an LED, you give electricity and you obtain light. In a solar cell, you shine light and this will generate electricity. And both are formed using PN diodes. Uh, So, what exactly how a solar cell functions is that when you shine light on it, it will generate electron hole pairs. And then what you do is you take that electron hole pairs outside you take the generated electrons and holes outside the PN diode. So you separate them, and then you can either use directly uh, to run your appliances, or you can store in electrochemical storage devices like batteries. So next question: a silicon PN junction diode emits which type of radiation when forward biased? Infrared, visible, ultraviolet, none. So the answer to this would be none, because a silicon is an indirect bandgap semiconductor, so it is not an efficient light emitter. Hence, it does not emit radiation. Instead, what it does it emits heat. In a PN junction photodetector, which region primarily dictates electron hole pairs when exposed to light? Which region primarily generates electron hole pairs when exposed to light? P region, N region, depletion region, ohmic region. So the answer to this would be depletion region. So the electron hole pair generation, when the generation happens inside the depletion region, and from there it's transported to the P and N regions for and it contributes current. So this is a simple numerical. A silicon photodiode operates at room temperature, that is 300 Kelvin. The reverse saturation current I naught is 10 power minus 12 amperes. What is the current at a reverse bias of minus 0.5 volts assuming an ideal diode equation? 10 raised to the minus 12 angstrom, 10 raised to the minus 6 amperes, 10 raised to the minus 10 amperes, 10 raised to the minus 9 amperes. This is a very simple question. So the answer to this is 10 raised to the minus 12. So actually you see we are in reverse bias. So at reverse bias the current is always the reverse saturation current only, which we have already given here 10 raised to the minus 12 amperes. So you did not have to do any calculation here. The the ideal diode equation that we study is valid for forward bias condition. So next question. The wavelength lambda of light emitted by an LED with a band gap of 2 electron volt at approximately 620 nanometer, 820 nanometer, 1550 nanometer, 310 nanometer. Anyone able to solve this? That is correct. The answer would be 620 nanometer. So you know the formula for calculating wavelength from energy is hc by E, and if you put these values you will get around 620 nanometer. There's a very shortcut method to calculate the to convert between energy and wavelength, which is you divide by 12, you divide from 1240. So like here the energy is given as 2 ev, so you divide 1240 by 2, you get 620. Similarly, if you wanted to calculate the energy for 820 nanometer, you will do 1240 by 820, and the answer would be the energy in ev. So in an LED, the energy light emitted would be equal to your band gap, and then you just convert this to wavelengths. Now a similar question: a gallium nitride LED has a band gap of 3.5. So in an LED, the band gap of the semiconductor is the wavelength that will be the wavelength of the light that will be emitted by an LED will correspond to the band gap of the semiconductor. Here the band gap is given U as 2 eV, so the emitted light will also have an energy of 2 eV. So now you just have to convert the energy of light to the wavelength of light, which you can do by this formula, this calculation, or a shortcut would be to just divide from 1240, 1240. So you do 1240 by 2 eV, which 1240 by 2, and you will get the answer in nanometer, which is 620. Similarly, similarly in this next question, which is a exactly same question, a gallium nitride LED has a band gap of 3.4 eV. What is the color of light it emits? Red, green, blue, infrared. Just use the trick that I just told you. That is correct. The answer would be blue. So if we divide 1240 by 3.4, you will get 365 nanometer. And 365 nanometer is in the range of blue and ultraviolet. So it is actually ultraviolet, but you can also see blue color. Okay, here the answer is shown to you. If a photodiode has a dark current of 10 nanoamperes and a photocurrent of 100 microamperes, what is its current ratio in illuminated versus dark conditions? 10, 100, 10,000 and 1000. So here you just have to do, you are given dark current 10 nanoamperes and photocurrent is 100 microamperes. So you just have to calculate their ratio. So you divide 100 microamperes by 10 nanoamperes, which is 10,000. This is a very simple question. And this is a very important part. So very important for photodiode, which is illuminated current, the ratio of between illuminated and dark condition is the main selling point of a photodiode, because you want to detect the change in current in a photodiode, and the higher the difference between the current is, the better the performance of photodiode will be, the more sensitive it will be. Hence you want this number to be as high as possible. A photodetector is illuminated with light of power 1 milliwatt and has a quantum efficiency of 50%. If the photon energy is 2 electron volts, what is the photocurrent generated? 0.4 milliamperes, 0.5 milliamperes, 0.3 milliamperes, 0.25 milliamperes. So the incident light is of power 1 milliwatt, and its energy is 2 electron volts, and the quantum efficiency of the given photoreactor is 50%. So you have to calculate the current generated. This is a slightly tricky question, so I will give you some time. So the answer to this is actually 0.25 milliamperes. So you first you need to calculate how many photons are being, what is the incident number of photons per unit per second. So which is simply power by energy. So you calculate power 1 milliwatt, energy is 2 ev, so you calculate by converting it to joules, and by that you will get 3.12 into 10 to the power 15 photons per second. Now this is the quantum efficiency is 50%. That means for every 100 incident photons will only generate 50 electrons. So the number of electrons hole pairs generated will be half, that is 1.5 in 10 to the power 15. Now the current is just, you multiply it with the current is just q into n. So you multiply 1.6 into 10 to the power 19 into 1.56 into 10 to the power 20 15, and you solve it, you will get 0.25 milliamperes. So this was a slightly tricky question because it involved knowing all these things. But this is the type of question you can get from a photo detector part. Next, the efficiency of a solar cell is maximized when it absorbs photons of which energy range? Greater than the band gap energy, less than the band gap energy, equal to or slightly greater than the band gap energy, and any photon energy is quite equally efficient. Yes, the answer to this would be C, equal to or slightly greater than the band gap energy. So if you shine light that is less than the band gap energy, then there won't be any absorption and no electron hole pair generation. So all that energy is going to waste it. If you shine greater than the band gap energy, then the then it will still absorb only the energy that is required to generate electron hole pair, which is equal to the band gap energy. So all that excess energy that you are giving is also going to waste. So to get most efficiency, only you should only give energy that is equal to the band gap energy, so that the electron hole pair generated, so that it is generated by absorbing all the incident photon energy. So no energy is going to waste. Next question. The fill factor for a solar cell is given by VOC by ISC, VMPP IMPP by VOC ISC, ISC by VOC, VOC by VMPP. Yes, so the answer to this will be B. So VOC is called open circuit voltage. ISC means short circuit current. So that is the voltage across the solar cell when there is no current flowing through. So that is called VOC, and that is basically voltage at zero current. ISC is the current, maximum current that flows when you short both the ends of the solar cell or you can say it is the current at zero voltage. So so all the all the data for solar cell lies between a square, that is a rectangle, that is formed by your origin, your VOC and your ISC. If you connect them, you will get a rectangle, and your current versus voltage value will lie between inside this rectangle, and the maximum maximum current at some so like the maximum current at maximum voltage is given as IMPP and VMPP, and so you divide these two values to get the fill factor between your ideal case and your actual case, and that gives you the efficiency of a solar cell. Next question, another slightly complicated numerical. A solar cell is illuminated under 1000 watt per meter square sunlight. If the area of solar cell is 10 centimeters square and efficiency is 15%, what is the maximum power output? 1.5 watt, 150 milliwatt, 1.5 milliwatt, 15 watt. Yes, so the answer to this will be 150 milliwatts. So you know the incident power is 1000 watt per meter square, and the solar cell area would be 10 centimeters square, which is 10 is to minus 3 meters square. So the power that is falling on the solar cell is 1 watt, and now its efficiency is given as 15%. So only that only that 1 watt input power is converted to 15% of output power, So calculate 15% of 1 watt, and that is your 150 milliwatt. So that is your output power. And this is the maximum output power, because there will be, there can, so the solar cell area is 10 centimeter square, but not all of them will be the sensitive part. So there can, the effective incident power can be even lesser than 1 watt. So this is the maximum power output you can expect from this solar cell, that is 150 milliwatt. The breakdown voltage of a diode is primarily determined by minority carrier diffusion length, depletion region width, surface recombination velocity, contact resistance. Which of these four determines the breakdown voltage? That is correct. The answer would be depletion region width. So, so the greater so the breakdown voltage is directly proportional to your depletion region width. The higher the depletion region width, the higher the breakdown voltage would be. Other three factors do not contribute to your breakdown voltage directly. So the Zener breakdown mechanism in a diode is due to minority carrier injection, quantum mechanical tunneling, impact ionization, diffusion of charge carriers. So the answer to this is actually quantum mechanical tunneling. Impact ionization is not the answer for Zener breakdown. Inside in Zener breakdown, at high voltage, the in Zener breakdown, your depletion region is very narrow, very thin. So at high voltage, your electrons and holes start tunneling through the depletion region, and hence you get a very high amount of current. Now, in an avalanche breakdown process, an electron gains sufficient kinetic energy and tunnels through the barrier, recombines with a hole, collides with an atom, creating more electron hole pairs, remains in equilibrium. So here the answer would be collides with an atom, creates more electron hole pairs. So this phenomenon is called impact ionization, where on higher voltage the electron would gain very high kinetic energy and it will collide with an atom and it will knock out an electron from the atom due to the impact, and it will ionize the atom. So that is called uh, impact ionization, and this will create more electron hole pairs, and they will further collide with another atom to create more electron hole pairs due to, and this way you will get a huge number of electron hole pairs, which will lead to a high current. This is avalanche breakdown, and the tunneling through the depletion region is your Zener breakdown process. So Zener breakdown only occurs in a very highly doped PN junction diode where the depletion region is very narrow. That it allows tunneling. So a silicon diode has a depletion width of 2 microns and a critical electric field of 400 kilovolt per centimeter. What is the approximate breakdown voltage? 20 volts, 40 volts, 80 volts, 160 volts. Yes, so the answer to this will be 40 volts. So your formula for breakdown voltage is half depletion width into critical electric field. So you just multiply those values and you get 40 volts. So you can see it's directly proportional to your depletion width. So higher the depletion width, the higher would be your breakdown voltage. The capacitance of a PN junction in reverse bias is due to majority carrier injection, depletion region acting as a dielectric, impact ionization, tunneling of carriers. That is correct. The answer to this would be depletion region acting as a dielectric. So the majority current injection is basically what happens in forward bias condition. Impact ionization and tunneling of carriers are breakdown processes, avalanche and Zener, as we just studied. So in a reverse bias, you have a big depletion region which blocks current, which is blocking your current. So it is acting as a dielectric. Hence, you are getting a capacitance. The capacitance of a PN junction in reverse bias follows the relation C is proportional to V, C is proportional to 1 by V, C is proportional to 1 by root V, C is independent of V. Yes. So the answer to this is C is proportional to 1 by root V. So the formula for capacitance in reverse bias PN junction is given by epsilon by W proportion, and this is proportional to 1 upon under root of V built-in potential plus reverse bias. So you can see the result is C is proportional to 1 by root V. So related question, in a 1 by C square versus voltage plot for CV profiling, the doping concentration can be found from the intercept on the voltage axis, the slope of the plot, the peak value, the capacitance at zero bias. That is correct. The answer would be the slope of the plot. So the doping concentration is calculated as minus 2 by q epsilon, and then the slope of 1 by c square versus v. So by from the slope you can calculate your doping concentration. What is the significance of the x-intercept in a 1 by c square versus voltage plot? Breakdown voltage, built-in potential, carrier lifetime, electron affinity. The answer to this is actually built-in potential. So the 1 by c square versus voltage plot is calculated for reverse bias, but when you interpolate it in the negative direction, so you will see that the plot will merge with the x-axis, and that value is corresponds to your built-in potential, which you can also see from here. So since so you plot you change it to 1 by c square, and so you will see here 1 by c square is then proportional to your vbi plus vr. So at at zero intercept, your it will give you your vbi. So next question, what is the main difference between a Schottky junction and a PN junction? A Schottky junction has a built-in potential while a PN junction does not. A Schottky junction is formed between a metal and semiconductor while a PN junction is formed between two semiconductors. A Schottky junction only allows forward bias operation, whereas a PN junction allows both forward and reverse bias operation. Schottky junctions do not exhibit rectifying behavior. Yes, the answer to this would be B. A Schottky junction is formed between metal and semiconductor, while a PN junction is formed between two semiconductors. So we till now we were studying PN junction diodes. So where you join a p-type semiconductor and an n-type semiconductor. Now what will happen if you join a metal and a semiconductor? So when you join a metal semiconductor, similar to how the Fermi level equalizes in the PN junction, in the metal and semiconductor also, the work function of metal will equalize with the Fermi level of the semiconductor, and that will give rise to a to some band bending, and depending on the work function difference, you you can get a Schottky junction. So what is the term used for a contact that shows linear current voltage behavior? Schottky contact, ohmic contact, diode contact, capacitive contact. That is correct. The answer would be ohmic contact. So when you join a metal and a semiconductor, there are two types of contacts that form: ohmic contact and Schottky contact. In ohmic contact, you don't see any rectifying behavior. You will see a normal ohmic behavior, which is V is proportional to I. So you get a linear current voltage behavior. So next question. For a metal semiconductor contact, Schottky behavior is expected when phi m is greater than phi s for n-type semiconductors, phi m is less than phi s for n-type semiconductors, the semiconductor is heavily doped, the metal thickness is very high. So in which of these cases will you get a Schottky contact? That is correct. The answer would be when the phi m is greater than phi s for n-type semiconductors. So phi m is the metal work function and the phi s is the semiconductor work function, or you can say the Fermi energy difference between Fermi level and the vacuum. That is the work function for your semiconductor. So so when your metal work function is greater than the work function of a semiconductor, in case of n-type semiconductors, this is important. Then you get a Schottky behavior, and in this case, you will get a ohmic contact. In case of p-type semiconductors, your metal work function should be less than your semiconductor work function to get a Schottky contact. Next question: which of the following metals is more likely to form an ohmic contact with n-type silicon? Platinum with work function 5.65, gold with work function 5.1, aluminum with work function 4.1, nickel with work function 5.5. So the answer to this is actually aluminium with work function 4.1. So yours the electron affinity for silicon is around 4 to 4.05. So for n-type silicon, your if you and your Fermi level you can expect around zero point 0.2 zero point 0.3 electron volts below your conduction band. So if you add that, you will have a you will have your work function for a semiconductor around 4.2, 4.3 or 4.4 ev. And we just read that for n-type metal, n-type, to get an ohmic contact, your metal work function should be less than your semiconductor work function, which in this case is only valid for aluminium. So you see, in silicon devices, you will see that gold, platinum, and nickel, all these metals are not used to make contacts. You either use aluminium or copper. So the next question: the depletion rich in a Schottky junction primarily forms in the metal, the semiconductor, both metal and semiconductor equally. The depletion region does not form in Schottky junctions. So the answer to this would be semiconductor. So you see the metal has a high concentration of free carriers, so it does not form a depletion region due to extremely high number of free carriers. So you can consider this you can consider a metal as a very highly doped semiconductor. So if you join a semiconductor, very highly doped semiconductor with a less doped semiconductor, you what you get is an abrupt p-n junction. And in an abrupt p-n junction, you know that, so in p-n junction you know that the depletion width is inversely proportional to your uh, to your carrier concentration, your doping concentration. So if you have very high doping, your depletion width will be almost negligible. Similarly, you can consider metal as similarly. So in your metal there won't be any depletion region. All the depletion region will be completely in the semiconductor part. Next question: the built-in potential of a Schottky junction is given by VBI equals to phi m minus phi s, VBI equals to phi s minus phi m, VBI equals to chi minus phi m, VBI equals to q VBI. That is correct. The answer would be VBI equals to phi m minus phi s. So the difference between the work function of the metal and the semiconductor gives you your built-in potential, and due to this built-in potential, you get a rectifying behavior in a Schottky barrier. Schottky junction. This built-in potential is called a Schottky barrier. So the work function of a metal is 5.2 electron volts, and the electron affinity of an n-type semiconductor is 4 electron volts. If the semiconductor has a Fermi level zero point 0.2 electron volts below the conduction band, what is the Schottky barrier height? 1.2 electron volts, 1 electron volt, 5.4 electron volt, 4 electron volts. So the answer to this would be 1 electron volts. So you see, your electron affinity is given as 4 electron volts and the Fermi level is given as zero point 0.2 electron volts below conduction band. So add 4 and zero point 0.2. So your work function for your work function for semiconductor comes out to be 4.2 electron volts. So you do 5.2 minus 4.2 and so you get 1 electron volts. In some cases, you will see the answer to be 1.2 electron volts because sometimes the Schottky barrier height is considered between the metal work function and the electron affinity of the semiconductor. It all depends what is the definition of the barrier height you are considering. Because in some cases your built-in potential and your barrier height is considered same, and in some cases your barrier height is considered the energy that electrons have to jump to go to metal, which so electrons are sitting in a conduction band and they have to jump to metal. So there you calculate the barrier height between the conduction band and the metal, which comes out here as 1.2 eV. So next question: if a Schottky diode has built-in potential of 0.7 volts and a depletion width of 100 nanometer, what is the electric field at the junction? 7 into 10 to 5 volt per centimeter, 7 into 10 to 4 volt per centimeter, 1 into 10 to 6 volt per centimeter, 1 into 10 to 5 volt per centimeter. So the answer to this would be 7 into 10 to the 4 volt per centimeter. So basically, you just have to divide the built-in potential with the depletion width to get the electric field, which is 0.7 divided by 100 nanometer. If you do that, you will get 7 into 0.10 raised to the power 4 volt per centimeter. Next question. Which statement is true regarding the depletion width in a Schottky diode compared to a PN junction diode? It is wider in Schottky diodes for the same doping concentration. It is narrower in Schottky diodes for the same doping concentration. It is same in both diodes. The depletion width in Schottky diodes is independent of doping concentration.
Answer would be C, sir.
Actually, the answer would be B. It is narrower in Schottky diodes for the same doping concentration. So see, in a PN junction, the depletion region is in both P side and the N side. Whereas in Schottky diode, the depletion region is only in the semiconductor side. Hence, the depletion region is shorter in the Schottky diode. What is the primary conduction mechanism in forward bias Schottky diodes? Diffusion of minority carriers, thermionic emission over the Schottky barrier, quantum tunneling, impact ionization.
C.
So the answer to this would be thermionic thermionic emission over the Schottky barrier. So your electrons are in the your conduction band of the semiconductor. So they have to cross the barrier to go to the metal side to conduct, or from metal they have to cross the barrier to go to the semiconductor. So that is called your thermionic emission, because the energy the energy is gained due to heat. So you see it's different from your PN junction diodes where the conduction is due to drift and diffusion. If a Schottky diode and a PN junction diode are used in a high frequency circuit, which one is preferred and why? Schottky diode because of its faster response time, PN junction diode because of its higher reverse breakdown voltage, Schottky diode because of its higher reverse leakage current, PN junction diode because of its lower forward voltage drop.
A and C, sir.
So the answer to this would be A. Schottky diode because of its faster response time. So the switching speed between on and off in a Schottky diode is faster than in a PN junction diode because only one type of carriers are are responsible for current in a Schottky diode. So there are no minority carriers in Schottky diode. Hence, it has a faster response time. And you want a fast response in a high frequency circuit. In an N-type Schottky diode, the depletion region is primarily composed of electrons, holes, ionized donor atoms, and free carriers. So the answer to this would be ionized donor atoms. So it's called depletion region. So it is depleted of your electrons. Since it's an N-type Schottky diode, so the depletion region is depleted of electrons. So the only thing that's left are your ionized donor atoms. Similarly, similarly as in a PN junction diode, your depletion region is only consisting of your ionized donor and acceptor atoms. So this is a numerical, very simple numerical. If an N-type Schottky diode has a built-in voltage of 0.6 volts and is reverse biased as -2 volts, what is the total potential barrier that electrons must overcome? 0.6 volts, 1.6 volts, 2.6 volts, 3.2 volts.
Answer would be C, sir.
That is correct. The answer would be 2.6 volts. So since it's reverse bias, so your total potential barrier will be the sum of your built-in voltage and your reverse bias voltage, which is zero point 0.6 plus 2, that is 2.6 volts. So you are so when you are giving it a reverse bias, you are increasing the potential barrier that you need to overcome. So hence that will reduce the current, or that will block the flow of current. Now similarly, if your built-in potential is zero point 0.8 volts and you are forward biasing it with zero point 0.3 volts, what is the new potential barrier? 0.5 volts, 1.1 volts, zero point 0.8 volts, 1.5 volts. That is correct. The answer will be zero point 0.5 volts. So in forward bias, you subtract the forward bias voltage from your built-in potential. So that would be zero point 0.8 minus zero point 0.5. So 0.5 volts. So now your potential barrier has reduced. So it will be easier for electrons to overcome the barrier. Hence you will have a higher current. In a thermionic emission model for Schottky diodes, the current density is given by J equals to A star T square e power minus q phi b by kt e power qv by kt minus 1, J equals to A star e power minus qv by kt, J equals to q nd mu e, J equals to sigma v.
Answer A, sir.
That would be correct. The answer would be J equals to A star T square e power minus q phi by kt e power qv by kt minus 1. So this you see is the same as similar to your current equation in your PN junction diode. So this would be your reverse saturation current, and this would be your for the equation for forward bias current, ideal diode equation. So here this A star is called a Richardson constant. This T is your temperature, so you can see it has a higher dependence on temperature. As temperature increase, your current will hugely increase. This is due to the current here is thermionic emission, so you will have at higher current the electrons will have more energy to cross the barrier. Hence, there's a t square dependence. Then your phi b is your built-in potential, Schottky barrier height. So this will be your reverse saturation current, and this will be your diode equation current. So if a Schottky diode has a barrier height of 0.6 electron volts and operates at 350 Kelvin, what is the ratio of forward current to reverse current at an applied bias of 0.3 volts? So if you what will be the ratio of the current if you apply a forward bias of 0.3 versus a reverse bias of 0.3? E raised to power 5, e raised to power 7, e raised to power 10, e raised to power 3.
D, sir.
So the answer to this will actually be e raised to power 10. So at in reverse bias, your current remains constant at your reverse saturation current, and your forward bias current is equal to your reverse saturation current multiplied by e power qe by kt minus 1. So since usually e power qe by kt is very great, much greater than 1, you can ignore the minus 1 part. So you will get if by ir as e power qe by kt, and you put all these values, which is for forward bias is 0.3 volts, and your Boltzmann constant and your given temperature 350 Kelvin. You calculate this, you will get this is equals this thing qv by kt will be equals to your 10. So the answer here you will get e power 10. So you see, this is your this is your current equation in your Schottky barrier diode. So this whole part is known as your reverse saturation current, which is constant for any reverse bias until breakdown, and this part is your forward bias current equation. So in case of reverse bias, only this you call this I naught. So your reverse bias current will be I naught, and your forward bias current will be I naught e power q by kt, ignoring minus 1. So you you do I naught e power q by kt divided by I naught. So I naught and I naught will cancel, and you will be left with e power qv by kt. And V here is given as your V is your forward bias voltage, which is here given as 0.3 volts. Your K by Q will be 8.6 into 10 to the power minus 5 electron volts per Kelvin. This is your Boltzmann constant in electron volts. That takes care of your Q. So you don't have to put Q here. And T would be 350 Kelvin as given in the question. So you calculate this, and this comes this comes around 10. So Q by KT comes around 10. So your E power Q by KT will be E power 10. So your answer will be E power 10. A Schottky diode has a Richardson constant of 120 amperes per centimeter square Kelvin square, a barrier height of 0.8 electron volts, and operates at 300 Kelvin. What is the reverse saturation current density Js? 5.8 into 10 to the minus 7 ampere per centimeter square, 4 into 10 to the minus 7 ampere per centimeter square, 2.2 into 10 to the minus 6 amperes per centimeter square, 1.1 into 10 to the minus 8 ampere per centimeter square. So we just saw the formula for reverse saturation current. So anyone got the answer to this? That is correct. The answer would be 4 into 10 is to the power minus 7. So the formula we had just seen, A star T square e power minus q 5 by kt. So 5b is given as 0.8. Since it's room temperature 300 Kelvin, you know kt by q is 26 milli electron volts. So you divide that and you get e power minus 30.9, which is 3.7 times minus 14. Then you multiply it with 300 square and 120, and the answer you get is 4 into 10 raised to the power minus 7 approximately. So that is what I had for today. Thank you for listening.
Thank you, sir.
As you can see here, the reverse saturation current for Schottky diode is actually greater than the current for PN junction diode. So in PN junction, this value is around 10 raised to the power minus 12. So in case of Schottky barrier, your reverse leakage current will be higher.
Sir, how to calculate e to the power minus 30.09 equal to 3.7 into 10 to the power minus 14? How to calculate, sir?
You use a calculator. That is, you can't calculate manually. This value might not be right. The value might not be right here, but if you calculate this, you will get around 4 into 10 to the power minus 7, 4 to 4.5 you will get depending on how, since it's very high value. So so even like if you take 25.9 millivolts or 26 millivolts, that will also create a huge difference here in the first decimal place, but approximately it will be 4 to 4.5 into 10 to the power minus 7 ampere per centimeter square. Don't look at this value, it might be wrong here.
Sir, this is the end of the question, sir.
Yes, the questions are here. So there is a question in the comments. So an n-type material with electron affinity of 4 electron volts forms a Schottky contact with a metal with work function of 5 electron volts. The n-type doping density of the material is 5 into 10 per 7 centimeters. Find out the built-in potential for Nc equals to 5 into 10 per 18 centimeters. So here you have to use the doping density and the Nc value to calculate your Fermi level. So like the question that I had shared here, yes. So here I had shared that the electron affinity I have given you 4 electron volts. In your question also the electron affinity is 4 electron volts, and the work function you are given 5 electron volts. For me work function is 5.2, so it's just you just have to use 5 electron volts as work function. So I have given you EC minus EF as zero point 0.2 electron volts, EF minus EC. So you have to calculate this value, which I have given you as zero point 0.2 electron volts. You have to calculate that value using your doping density and NC value, which you have studied in your previous previous 2 weeks. If you take out the notes for previous 2 weeks, you will find the equation to calculate your Fermi level, and using that to calculate the work function of the your semiconductor, and then you just have to do phi m minus phi s, and that will give you the answer.
Yes, sir. Okay, sir. Good night, sir. Thank you.
Thank you. Thanks for listening.